This is lesson 3 in chapter 7. We're going to look at Euler's method today. You know, in Calc AB, we talked about differential equations and we used slope fields in order to approximate or sketch curves based on the slope fields. In this lesson, we're going to look at a numerical approach called Euler's method, where we can go from point to point, given some information, and make an approximation for possibly a differential equation that can't be solved algebraically. So let's say, for example, if we just start out right here, if we know this point, we can find the slope of the tangent line. And I'm just going to kind of review about the procedure here. So we want to find the slope of the tangent line. And then we can go to the second point using that slope. So it'll get us a second approximation after we found the slope of the tangent line. And we know that the change in y, that's going to be about the slope of the tangent line times the change in the x. So this is the key to using Euler's method. And here in this example, you see the nice smooth curve. This would have been the exact solution when we found an algebraic method. Exact solution curve, SOLUTION. And this curve here would be our Euler approximation. So named after Leonhard Euler. There you go. Okay, so let's jump right in. So the big idea of Euler's method is that we're going to use local linearity, and we're going to be zoomed in sufficiently small neighborhood around that point of tangency so that we can use that small neighborhood to calculate the slope at the point using the differential equation. And the slope's going to tell us the direction to travel on some small segment, which is going to be our delta x. And if you move a small amount and calculate a new slope from whatever differential equation we're given, we can travel another small distance, and we just repeat that process until we've found an approximation to the actual curve. So it's just one method or one approach, a numerical method for solving a differential equation. So let's say we want to start off, and I'm going to remind us of the equation for the tangent line. So y is equal to y sub naught plus the derivative, or the slope of the tangent line, times the delta x. And that's what we're going to use here in the tangent line. And the slope is our dy dx. And we're going to take the change here and we're going to plug this number into the tangent. So we're going to plug this number into the tangent, and it's going to give us this new y value. So they've given us something to start off with. They've told us that when x is 0, y of 0 is 1. So we know we're going to go 0, 1 is our ordered pair. And they're telling us that the slope, dy dx, is the y value, so that would be 1. So if we used this equation for the equation of our tangent line, then our equation for our tangent line would be y equals x plus 1, since the slope is 1 and the y value is 1. And we want to go up. Our delta x is going to be increasing by 1/10. So it's a small increment, which will give us a good approximation. So since our y value was 1 and we added 1/10, our new y value is 1.1. And that would go right here. Okay? So like they said, we're going to go up on our x's by 1/10. So we'd go up 1/10. And the slope is the y value, which is 1.1. So we've gone up 1/10, and now we've gone up another 1/10. So the easy way, I know this is kind of complicated to write the tangent line each time, but if you do, you're writing the slope, which is 1.1, times x minus the x value, which is 0.1, plus the y value, 1.1. And if we substitute 0.2 in there, then basically what we're doing is we're taking the slope times the delta x, which is 0.2, see, plus the initial y value, which was 1.1. So if we did that mathematically, we're going to end up with 1.21. Only let's go back. We got to fix this. Not up 0.2, up by 0.1. This is our delta x. Our delta x is going up by 1/10. Okay, so going up 1/10 again, we're going to go up. That would be, now we're at 2/10, and our new y value is 1.21. So our slope is the y value, which is 1.21, and the equation for the tangent line is 1.21 times x minus 2/10 plus 1.21. And now we're going to go up again. So once again, if we have 1.1, now we're at 1.21 times 1/10. So where were we? We got 1.21, which is our slope, times our change in x, which is 1/10, plus the y sub naught, which is 1.21. So this times this times the 1/10 gives me my new y value, 1.331, which now becomes my new y value when I step up 1/10 here. Okay, so you see the procedure, and our slope is going to be 1.331, and the tangent line would be 1.331 times x minus 3/10 plus 1.331, and our delta x would go up to 0.4. And then we could calculate 1.331 times 1/10 plus 1.331. And using our calculator, our new value is 1.4641. So going up 1/10, we've got 1.4641, which is also our slope, and the equation for the tangent line is 1.4641 times x minus 4/10 plus the y value, 1.4641, which puts us at 1/2, and changing this process, we end up with 1.61051, and so on and so forth. 1.61051, which is also our y value, and the equation for the tangent line times x minus 1/2 plus that 1.61051. We're substituting 0.6 in here, and if I write this last step out, substituting 0.6, we have 1.61051 times 0.1 plus 1.61051, and our final approximation looks like that. So we're moving increments of 1/10 each step, and we're tracing out the differential equation 1/10 as the change in x moves 1/10 to the right each time, and the slope of the tangent line is the y value, and to get that new y value, we're following this tangent line equation. So that's the plug and chug approach to figuring Euler's method. So here we have Euler's method. We can solve the differential equation for dy in terms of x, y, and dx. And we can substitute values of x, y, and dx to calculate a value for the change in y. And the change in y is going to be the slope times the change in x. And we found the approximate new value of y by adding the change in y to the previous y value. So this is what we did on the table. So the trick is to use each old approximate xy ordered pair to be able to calculate each one of the new approximate changes in y. Okay? So that's the procedure. In this one, we want to show that Euler's method for dy dx is a half times x plus y, starting at 2.2, 1.11, and using two steps with the delta x 0.005, that it's going to give us this value when we get to 3/10. So if we add 0.05 to 0.2, then we're at 0.25. And we had 1.1, so we want to take that delta x, or this equation, dy, 0.5 times 0.2 plus 1.11, and multiply it by the delta x, 0.05. So with our calculator, we get a new y of 1.14275. So verify that I didn't mess up on that. So this is my new y, 1.14275. So following that same procedure, I'm going to take the 0.5x, x is a quarter, plus y, 1.14275, and multiply it by the change in x, which is 0.05. And we get 1.17756, which is what we want when we get to 0.3. So we want to add 0.05 or 5/100ths to 25/100ths, which is 0.30, and we ended up with 1.1775. So we don't need to go any further, and we have shown by Euler's method that the function f of 3/10 is approximately 1.1775. So we used Euler's method with the given differential derivative at the starting point and the step up, or the step to the right, of 5/100ths. In example 2, we're going to approximate 4 points on the solution curve to dy dx is negative 3x squared y, starting at 0, 2. So we're starting at 0, 2. We're moving our x's up 1/10 at a time. So our first new x is 0.1, and we have the formula negative 3 times x squared. So our x was 0, and our y was 2, and we're multiplying it times 1/10, which is our step, and that gave me 2. So again, we have 1/10 and 2. So we're stepping up 1/10 because this is going up by 1/10 each time. This would step up to 0.3, and this would step to 0.4. And we're following the slope. They're telling us what to do. The change in y is the slope of the previous times the change in x. So negative 3 times the previous, which is 0.1 squared, times the y, which was 2, times the change in x. And that turned out to be 0.006. It's negative. So if we had 2 and we subtracted 0.006, that's going to leave us with 1.994. So our third point is 1.994. And I'm doing this on the side with my calculator. So 0.3, we're going to go negative 3 times the previous, which is 0.2 squared, times the previous y, which was 1.994, times the delta x. And we're taking 1.994 and we're subtracting to get 1.970072. So our fourth point is 0.3 and 1.970072. And then the last one is negative 3 times 3/10 squared times our previous y times the delta x, and all of that subtracted from this gives us 1.9168800. So the final point on the approximation is 1.916880. So remember, these are numerical methods for calculating points on a differential equation that possibly can't be solved algebraically. Here, the accuracy of Euler's method, the error in using Euler's method is the exact value minus the approximate value. If the number of steps used is n, the error is approximately proportional to 1 divided by n. So if you ever need to calculate the approximation, let's see, do we have, we have some calculator steps coming up. So let's look, compare the tables below. Each represents the specific solution to the differential equation dy dx equals y, where we started out at 0, 1 for our initial condition, and the delta x was a tenth. Euler's method is an approximation of the particular solution. So we want to take a look at what's going on with these two tables. And I believe I need to make a dual page here so we can see things side by side. Okay, so the graph illustrates the particular solution as it compares to the Euler approximation. So here's our solution curve, and here with the dotted points on the Euler approximation, you can see what's happening. We did our delta x was a tenth, and each time we moved a tenth to the right, the solution curve looked like that. So why do the approximate y values underestimate the actual values? Can you come up with a statement that would help you with that? So I would think about looking at this. This is our exact values. The function is e to the x, so we know that function is concave up. And these are our Euler approximation. So I would say something along this line. I kind of said it this way. Each tangent line will lie below the curve, since the solution curve to y equals e to the x is concave up, and we used the tangent lines to obtain our approximation. So that's why it's going to be below the curve, because of that concavity. In part B, we want to complete the table comparing the difference between the exact value minus the approximate value. And are the approximations getting better or worse? and y. So we want to look at the exact value of 1 minus 1, and 1 minus 1 is going to give us 0. And then in the next one, we got 1.10517, and we're subtracting 1.1, so we're getting roughly 0.00517. And I'm taking those numbers off of the table back here, comparing this minus this, and this minus this, all the way down. So you may want to turn off the video and come back to see if you get the same results as I have. So I had that for 2/10 and this for 3/10, 4/10, and 5/10. So complete the table. What can be changed? They're getting closer. They're getting worse because e to the x starts to grow more quickly, aren't they? So what could be changed to make Euler solution curve more accurate? I would say we could make the delta x needs to be smaller to make it more accurate. And then on this last page, these are how to use the TI Inspire calculator. So this is just a little tutorial for you. On the TI Inspire, you want to explore both the slope field and the approximate solution for dy dx is y minus 2x at the ordered pair 1, 2, with our delta x being 0.25. So the procedure below is how you go about doing that. So you'd want to go to a Scratchpad graph window and then click 3 and then click 8. That will lead you to this differential equation. And we want to enter the differential equation and the initial condition. So we're saying that y1 is the slope field, and our slope field was y1 minus 2x. So I had to put y1 in there. And the initial condition was 1, 2. So you can see I put the ordered pair 1, 2 here. Okay, so we went 3 is graph and 8 is differential equation, and it popped up this screen for you to enter the given stuff that they established here. So next, you want to put the parameters in to meet the step of a quarter. So if you click Tab and then up arrow, you're going to hover over the 3 horizontal dots at the right of the equation entry line. And the solution method is going to be Euler. And we want to scroll up to the plot step and change the default to a quarter and then click OK. So here's where I found my method is Euler. And I went to differential equation plot step and changed it to a quarter there. And then the last thing you want to do is click the menu button. So if you click menu, you can go down to trace, which is 5, and over to graph trace, which is 1. And we can use the right and left arrows to trace through the steps of a quarter. And you can see here on the right how it has traced out the steps. And the value approximations will display at the bottom of the screen. So you can see the initial condition at 1, 2. Here that is. That's the initial condition. And you want to see what happens when you edit the parameters to a half or to a tenth. And you should see how they are either skewed or draw closer to the actual curve. So this is just a good technique to check your Euler approximations when you're working on homework and such. It won't be something that you're required to do on the AP exam. They don't test your calculator knowledge. So that's the end of Euler's method. It's just a little tedious. See you next time.